Hello everyone, I'm Anirudh. I'm from Chennai. I'm a third year undergraduate student currently in the Department of Computer Science and Engineering at Indian Institute of Technology, Kharagpur. Right. Today I'll be taking the chapter General Organic Chemistry, that is Organic Chemistry, some basic principles and techniques. Right. So this chapter I'll be providing a brief first. Right. This chapter is basically intended to provide a general introduction to the techniques, to the principles of organic chemistry, what they are, what the nomenclature of different compounds are, how you actually identify if a compound is organic or if it's inorganic or something else, right? You get to know why exactly carbon holds such an important place in organic chemistry. You get to know what the different bonds are and how they are actually important in reactions, how they interact with reagents, etc., etc. Right? You get to know the different representations. You get to know the different some different nomenclatures. That is the aliphatic and the aromatic nomenclatures. You get to know what they are, and you get to know how you separate these compounds, right? You get to know how you purify, separate, and how you basically interact physically with these compounds. Because chemical reactions are not only chemical, they are also physical processes, because there are different phases. You have a liquid, you have a solid, you have gaseous, and you have solutions of those, right? You have to know how to purify and how to separate those phases, because sometimes in reactions what happens is you get a solution and you have to just separate the pure compound out of, right? In solutions, you have impurities and you have to know how to deal with this, right? Those things you'll be running this chapter. Finally, you deal with the different estimations. That is the how you actually quantify if some element is present in a given organic compound, right? And you get to see how exactly you determine how much of that compound is how much of that element is present in the compound, right? In the form of percentages or in the form of molar masses, whatever be it. But you get to know how you estimate the number of atoms of nitrogen in some compound, in some given organic compound, let's say aniline or something, right? Those things you get to know this chapter. So I'll not be dealing with the solved problems, because solved problems already have answers to them, and you can basically look at the book and go through it, right? Do not skip those, because there are lots of things in those solved problems that you need to look at, right? I'll directly be jumping into exercises. Just give me a moment to, question number 1. The hybridization states of each carbon atom in the following compounds, right? You're given 5 compounds here. One is CH2 double bond C double bond O. That's CH2 double bond C double bond O. This is actually called a ketene, right? You won't have this. This is not really important for the chapter, but this is just extra information. This kind of a compound is called a ketene, right? It's not a ketone. It's not an O. It's an E, because you have a double bond C double bond O here, right? This basically everybody knows that if it's a CH2 double bond, then this carbon has an sp2 hybridization. Since there are 2 pi bonds over here and just 2 sigma bonds, this carbon has an sp hybridization, and you are not asked hybridization state of O here. But even if you are asked for it, it's basically sp2, because O only has a pi bond, and you have 2 lone pairs over here. They are occupy 2 orbitals, right? So this has an sp2 or hybridization. This is sp, and this is sp2. Right. The second compound here over here, that's CH3, CH, double bond CH2, right? Pretty easy to see that this is your basic propene, right? Or propylene, whatever you want to call it, right? Both are the same, but this is IUPAC, propylene is more colloquial, right? So this compound, again, everybody knows that CH3 is sp3 always, right? Nothing to think of, nothing to worry about. CH3 means sp3, right? Here is CH double bond, single pi bond. So this is sp2, because there are 1, 2, and the CH sigma bond. There are 3 sigma bonds. So you have an sp2 hybridization, and here again it's CH2 and a double bond, right? So 1 pi bond, 3 sigma bonds. Again, this is sp2. Right. The third compound, that's a CH3 pi CO, right? This is your this is the simplest ketone possible. As acetone or 2-propanone or propanone is the same, right? You can't have any other place of a place of CO in propanone. So it's basically propanone or 2-propanone or acetone, whatever you want to call it, right? This again, this is same rules as before. This is sp3, this is sp3 because they are two terminal C and CH3, right? So they have to have 4 sigma bonds. So their hybridization has to be sp3, right? And this carbon again has 1 pi bond, 2 or 3 sigma bonds. This is sp2, right? And if you're asked for O is also sp2 because 2 lone pairs, 1 orbital, 2 orbitals, 3 orbitals that are involved in hybridization, and 1 pi bond, right? So this also is sp2, but that's not ours. The fourth compound over here, that's CH. This is CH2. This is CH and single bond C triple bond N, right? Everybody knows that CN is a triple bond, right? And you have bonds between carbons only, not between H and C over here. That's just stupid to think of, right? So you have this kind of a output. This basically, right? I'm not going to deal with the nomenclature over here, but it's propylene nitrile. Here again, we're dealing with the same rules. It's sp2 because there's only 1 pi bond. This has 1 pi bond only. This also sp2, right? And this is 2 pi bonds and 2 sigma bonds. That is sp, right? Nitrogen again has 2 sigma bonds, 2 pi bonds. This also sp. If somebody asks you for it, if nobody asks you, then you don't need to do it. Finally, coming to C6H6. C6H6 is benzene, right? You can represent it in this ring format, or you can represent it as this form or as resonance image, whatever, right? Each vertex is a carbon, as anybody who has studied bond line formula will be able to tell you, right? And since every carbon has one single pi bond, every carbon, you can count it, right? This carbon has 1 pi bond, this carbon has 1, this carbon has 1, this carbon has 1, this carbon and this carbon have this one, right? Since every carbon has 1 pi bond, every carbon has the sp2 hybridization, every carbon, right? There's no carbon is an exception here. Every carbon has sp2, right? That's the specialty of benzene. And this benzene, why you represent it as a ring is because these pi bonds are not static. They keep moving between their resonance images like so, right? Since I've drawn that, I'll draw this resonance image, and these two coexist in a solution, right? You can't separate these two forms out. Never can you separate these two forms out. They're not like your enantiomers in that aspect, where you can separate the L and D, the S and R images, but you can't separate two resonance images. They coexist in a solution, and so you represent it as a ring because each bond has characteristics of both the double and the single bonds. There should be a passage in between the chapter. If it's not here, then it should be in some other chapter. I don't exactly remember which, but there's a passage dealing with this resonance form where they actually tell you that the bond lines, they differ, right? For a single bond, it's about 139 or something. For a double bond, it's around 110 or something. And in benzene, it's an intermediate value. It shows that each bond has a characteristic of both the double and the single bond, right? So you usually represent it as a ring. That's the reason, right? Going to question number 2. Indicate the sigma and pi bonds of the following molecules. C6H6. Here you have to draw the molecule out. You have to know how to actually draw the molecule out, right? I'm going to be dealing with bond line formula over here, but wait, no. Since I have to indicate sigma and pi, I have to draw the whole thing, right? So it's a C, 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 and it's a C. It just kind of works, right? I'll just deal with one resonance image because is the same for both, right? Each is linked to an H, one H, and an H, right? Here you see that this is a pi bond, this is sigma, this is sigma, this is also sigma, this is also sigma, right? This is a sigma, 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 and this is also a sigma, right? And this is a pi, this is a pi. So you can basically see that there are 6 sigmas and 6 CC sigma bonds, 6 CH sigma bonds, and 3 CC pi bonds, right? That's the structure of benzene, basically, right? You have to note that if there's a double bond, one of those bonds is a pi and the other is a sigma bond. It's never the case that both bonds are pi bonds, right? Just remember the fact, because sometimes, even though you may know it, you may forget it. The second compound, that's C6H12, right? C6H12. Actually, before I have started drawing, I should have told you that I think there is a formula to find out if the compound given as such, right, in this numeric form, there is a formula to find out if this is fully saturated or if it has some unsaturation. It's called the degree of unsaturation, and it deals with the number of hydrogens into something. Wait, is it's some formula. I don't exactly remember what the thing is, but I think if you search for degree of unsaturation, I just write it down here. Degree. I don't exactly remember the formula, but if you actually search for this on Google, maybe you should get it, right? This formula will tell you how many cycles or how many double bonds or triple bonds you have in your compound that's represented in this numeric way, right? So, for example, if CH12 is given, then you will have a degree of unsaturation of 1, right? Because it's 2 hydrogens less than C6H14. That's your fully saturated alkane, right? So that degree of unsaturation can be represented as a double bond or as a cycle, right? Both are okay. But I'm taking the cyclic representation of C6H12 because I feel that since this was also a cycle, then this is also a cycle. But it doesn't necessarily need to be that. It can also be an unsaturation. And if it's a double bond, then the number of sigma and pi bonds will differ, right? That's something you have to note. So I'll basically giving you both forms, and I'll tell you what the number of sigma and pi bonds are, because for this question, the whole question itself is ambiguous, right? Here you have 2H again. Here you have 2H again. Here you have 2H, and here you have 2H, right? You can see that there are no pi bonds. Everything is sigma. So I'm just going ahead and writing everything is sigma, right? The cycle I'm writing inside and outside for the H. This is sigma, this is sigma, this is sigma, this is sigma. This is a sigma, this is a sigma. It's also a sigma, this is also a sigma. This is also a sigma, and this is also a sigma. So basically you can see that there are 12 CH sigma bonds and there are 6 CC sigma bonds, right? 6 and 2 per carbon, right? The other way this compound can be written, the same C6H12, is in this form. I'm not actually expanding it. This is CH3, CH2, CH2. That makes 3 carbons. This is CH2. That's the 4th. This is the 5th, and this is the 6th. Right? You can count the number of hydrogens here. This 2, this 4, this 6, this 8. This makes 9, and 9 plus 3 is 12. You have C6H12, right? So you can see that this kind of this compound is also a valid representation for C6H12, and this has 3 sigma bonds over here. This is 1 sigma bond. There are 2 sigma bonds over here, CH. This is another sigma. There are 2 sigma bonds over here, CH. This is 1 more sigma. And you have 2 sigma bonds over here, that's CH. This is another sigma. You have 1 sigma bond here, 1 sigma, 1 pi over here, and 2 sigma bonds over here, right? That makes, again, that makes 12 CH sigma bonds, 5 CC sigma bonds, and 1 CC pi bond, right? That brings the total number of that brings the number of bonds to 18. Same as before, but you see that there is a pi bond over here. Well, there was no pi bond over here, right? But the ring is also counted as a degree of unsaturation. That's something new, right? So right, that takes care of the second part. Then you have CH2Cl2. CH2Cl2, right? CH2Cl2, you can see that there are no double bonds. There is no lone pair sharing or some weird phenomenon of that sort. So basically, everything is a sigma bond, right? There are 2 CH sigma bonds. there are two C, Cl, sigma bonds, right? Nothing else. I'll just draw Cl properly, right? Nothing else. For sigma bonds over here. Then the fourth one is CH2, CCH2. This kind of a compound is called an alene, where you have double bonds one after another, right? One carbon connected to two double bonds on either side. This kind of a compound is called an alene. Allen, right? Kind of comes from all ene, but it's not exactly the nomenclature. You can maybe think of it that way, right? CH2 double bond C double bond CH2, right? You can see that every carbon is sp2 hybridized. Oh no, this is sp2, this sp, and this is sp2 hybridized, right? Because there are two sigma bonds, right? I'm just making that from 8.1 with this 8.2 over here, right? You have spread is representation H, and over here you have C, H, right? Sigma, 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 pi, sigma, pi, sigma, sigma, right? Because double bond, one of them is pi, one of them is sigma, right? So you have here, count with me, 4CH sigma. You have 2CC sigma, and you have 2CC pi. Wow, that's beautiful, right? Or 2CC sigma, 2CC pi, 4CH sigma bonds, right? Second last, CH3NO2, that's nitromethane, right? If you have all studied your nomenclature properly, this is nitromethane, right? This basically is split as 1, 2, 3, H, and H, and finally you have NO2, right? I usually represent the coordinate bond with an arrow. Even if you don't, it's fine. It's a single bond, whatever be it, right? But remember the lone pair. Remember the lone pairs, right? Usually, some people represent it as a plus and minus, but if you want to do that, you can. Doesn't matter, right? NO2 has two resonance structures. Remember that, right? This double bond can transfer between this O and this O. Again, the bonds share the same property with benzene, that these bonds are intermediate between a single and a double bond. They represent, they display an intermediate string, they display an intermediate bond length, and they display an intermediate electron sharing effect also, right? So here, notwithstanding those talks, basically 3 sigmas, one more sigma, and this is barely a sigma. I mean, this is not exactly a sigma bond. You can't really call it as such, right? And this is a pi bond, right? Some people think that this is a sigma bond, right? Maybe in some weird sense, you can maybe touch your nose through your legs and say that it's a sigma bond somewhere somehow, but it's not. This bond is special. It's a coordinate bond. It's a coordinate. It's not a coordinate bond. It's a coordinate covalent bond, right? Also called a dative bond. DATIV. Anybody who has studied chemical bonding will be able to recognize these names, right? This is a dative bond, right? This is not sigma, because sigma is created when two orbitals overlap each other head-on, right? But a coordinate covalent bond is formed when one atom completely donates its electron pair to another, right? It's not formed by orbital overlaps. It's formed by the donation of an electron pair to another, like a Lewis acid Lewis base reaction, right? It's a dative bond. It's not sigma, right? So finally, you have 3CH sigma. You have 1CN sigma, and you have 1 NO sigma, 1 NO pi, and 1 datum. 1 datum, right? That's nitromethane. And finally, you have HCO and HCH. Bonus points if someone actually knows what this functional group is. And I'm not going to say it. Right. So here you have this is sigma, this is sigma, NH, wait, this is sigma, and these are 3 sigmas held together, right? Because CH3, CH, 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 I'm not drawing it out. right? And this CO has 1 sigma 1 pi bond. So finally, the bond split is there are 1, 2, 3, 4 CH sigma bonds. There is 1 CN sigma bond. Wait, there are 2 CN sigma bonds, 1 and 2. There is 1 NH sigma bond, right? And 1 CO sigma bond, 1 CO pi bond, right? You can see that 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is 4, 6, 7, 8, 9. Right? 9 both are accounted for. And this is basically an amide for whoever is actually curious about it. All right, that finishes 8.2. Going to the third question. Write the bond line formulas for A, isopropyl alcohol, B, 2,3-dimethyl-butanol, and C, heptane 4. Right? Bond line formulas, give me a second. First is isopropyl alcohol. The isopropyl group is this, right? Where here is your water is attached to, right? Isopropyl is propane to whatever, right? And alcohol is OH. So basically this is your bond line formula for isopropyl alcohol. That is 2-propanol, right? Or propane to all, whatever. Nobody cares about how you write it, right? That is isopropyl alcohol. And you have 2,3-dimethyl-butanol. First, write down butanol. Butanol is, right, the bond line formula for butanol, simple butanol, is 1, 2, 3, 4, double bond O, single bond H, right? Since it's 2,3-dimethyl-butanol, this is 1, this is 2, this is 3, this is 4th carbon, right? That's the numbering because the aldehyde group has highest preference over here, right? Since it's 2,3-dimethyl, you add a single line at 2, you add a single line at 3. This is 2,3-dimethyl-butanol, right? And finally, you have heptane 4-O. Again, first draw the aliphatic chain that's given. That's heptane. 1, 2, 3, 4, 5, 6 makes hexane, and 1 more gives heptane, right? Since it's heptane 4-O, you can a number from whatever end, nobody cares, right? This is 5, this is 6, and what is left is 7, right? And so since it's heptane 4-O and ketone is a double bond O, add 4, make a CO, right? So this is the structure for heptane 4-O. Right? I'll write this is 2, 3 dimethyl butanol, and this is damn. That takes care of 3. Going to the fourth question. You have the IUPAC names for the following. A is you can see that this is a propane chain attached to a benzene ring. So this is basically 1 propyl benzene, or you can say it's this is propyl benzene, right? Because since there is only 1 attachment, everybody knows that this is attached at the first position, because in a benzene ring you can switch any carbon can be 1, right? This is an O, this is a P, this is propyl benzene, right? Sorry for my shoddy handwriting again, but it's hard operating a mouse over here. The second compound is this is a nitrile. This is a methyl at 1, 2, 3 position, right? Remember that the carbon in a nitrile has the first position. It's not this carbon that has 1, right? You have to be very careful in that. When you're writing cyanide, then this carbon has 1. If you're writing nitrile, then this carbon has 1, right? Be very careful in your nomenclature systems. That is a place where most people get tripped up, right? So this is basically 3-methyl. This is pentane, right? This is pentane nitrile, right? You don't use cyanide when you're dealing with IUPAC, right? Cyanide is your colloquial nomenclature, is the local nomenclature. It's not IUPAC. This is 3-methyl pentane nitrile. Then you have the compound C, which is this, right? Count 1, 2, 3, 4, 5, 6, 7. That's heptane. This is 2, 3, 4, 5, right? So this is 2, 5 dimethyl. Some people may think what happens if I count from here, maybe that'll give a more correct answer. But basically you can see that this first thing is at position 3, right? And here the first thing is at position 2. It's the lowest set of locums rule. If you have a 2 and if you have a 3 and both are the same substituent, then you go with 2 first. Right? So it's 2,5-dimethylheptane and not 3,6-dimethylheptane. D gives me this compound. That's again 1, 2, 3, 4, 5, 6, 7. Again a heptane chain. But here you have a 3-chloro and a 3-bromo, right? You have chlorine and bromine attached at the third carbon. So this is since you go with alphabetical order over here, it's 3-bromo, 3-chloro, heptane, 3-chloroheptane. And find the second last compound E is this carbon is attached to chlorine. This carbon is an aldehyde. You have 3 carbons finally. So this is a propanal and a chlorine attached at 1, 2, 3 position. Right? This is third position. So this is 3-chloro, again 3 propanal, right? 3-chloropropanol. Right? And finally, you have F writing at the side. Right? You have F, that's Cl2, CH2, CH, and a CH2 and an OH. Right? Split like this, you can see that there are 2 carbon atoms. It's ethane. There's an alcohol which takes precedence over chlorine. So this is ethanol, right? And this is carbon 1, this is carbon 2. You can see that there are 2 chlorines attached. So it's a 2,2 di-LORO dichloro HANOL, right? 2,2 dichloroethanol, right? That takes care of question number 4, right? Just display the answers again, right? 6 answers. Finally, you have question number 5. You just pause the video and check out these answers. Pause the video of your section before. Right. Question number 5 is, which of the following represents the correct IUPAC name for compounds? So I'll be drawing the compounds and I'll be discussing why each name is correct or each name is wrong, right? This is 2,2-dimethylpentane or 2-dimethylpentane. They're asking which one is correct. Right? So I'll leave it. We have a dimethylpentane, that's for sure. They just the question is just between if it's 2,2 or if it's just 2, right? Everybody knows that since it's dimethyl, there has to be 2 positions. So it's 2,2. That's for sure. But I'll also draw it out, right? A bond line formula only. I'm not dealing with the expanded formula. It's just bond line, right? It's 1, 2. It's 2,2 dimethylpentane, right? You can because there are 2 methyls, you have to have a position. You have to have a locant for each methyl group. So this is 2,2. It's not just 2, right? Just 2 has makes sense for 1 methyl. Does not make sense for 2, right? Question B, that's 2,4,7 trimethyloctane or 2,5,7 trimethyloctane. Let's draw it out, right? That's 5, 6, 7, 8. That's octane, right? This is 1, 2, 3, 4, 5, 6, 7, and 8. Right? Since you have since it's a contention between 2 things, I'll draw this 2. 3, 4, 5, 6, 7, and 8. Right? You are given 2,4,7 trimethyloctane, 2,5,7 trimethyloctane. It's 2, 4, 7. This is 2, 5, and 7. Right? You can see that here it's 1, 2, 3, 4, 5, 6, 7. From the other side, it's 2, 3, 4, 5, 6, 7. Right? So basically, if you take the numbering from the other side over here, you can see that this carbon, this becomes 2, 4, 7 again. It's 2, 5, 7 is the wrong nomenclature because both the compounds are the same. Right? Both compounds are the same. And so you deal with the lowest set of locants rule. A is 2, 4, 7. B is 2, 5, 7. 2, 4, 7 is the lowest set because 4 and 5 are in contention. 4 is less than 5. This is the lowest set. So this is the correct nomenclature. This is the wrong. right? So for the second question, this is correct. The first question, this is correct, right? And for C, it's 2-chloro-4-methylpentane or 4-chloro-2-methylpentane, right? Pentane, that's 1, 2, 3, 4, 5, right? You are given 2-chloro-4-methyl, or they're asking if it's the other way around, right? So if you want to think for a few moments, just pause the video and think for it, right? The answer here is the first nomenclature, that is 1, 2, 3, 4, 5 going to this side. That's correct, right? The other way around, this way is wrong. Why? It's because chlorine has greater precedence over a methyl group. I'll just write this methyl group because it's up, right? 2-chloro-4-methylpentane is the correct way, right? And you basically also go in the alphabetical order of the substituents, right? So chlorine first, methyl second. That's also something you have to take care of. You can't write 4-methyl-2-chloro. That's wrong, right? And the last question, D, is but 3-ine-1-ol, but 4-ol-1-ine. So this is butane, 1, 2, 3, 4 carbon and 1 OH, right? It's a 1-ol, and you have this is a 3-ine, right? Yeah, but 3-ine-1-ol. If you go through, if you go to this kind of a numbering system, that's but 3-ine-1-ol, right? The other way around is 1, 2, 3, 4. That gives you a but 1-ine-4-ol, right? But you know that alcohol group has higher precedence over an alkyne. And so this is what is correct. Again, this is correct. I think I forgot to highlight this, right? This nomenclature is what is correct. This is wrong, right? Because alcohol has precedence over an alkyne. If you see the rules, it's basically that the principal group, the principal functional group has a lower group. That takes care of 5. Then going to question number 6. Draw formulas for the first 5 members of each homologous series beginning with the following compounds. A, HCOOH. This is the homologous group of your alkene, straight chain carboxylic acids, right? The first member is methanoic acid, HCOOH. The second is ethanoic acid, that's CH3COOH. The third member is propanoic acid, that is CH3CH2COOH. The fourth is butanoic acid, that is CH3CH2CH2COOH, right? Then finally comes pentanoic acid, that is CH3CH2. Oh, can I condense it? CH2CH2COOH, right? The first 5 members of your straight chain carboxylic acids, right? The second B is basically the ketone or the homologous series of ketones, right? The first ketone is acetone, or it's propane-2-one, that is CH3COCH3. The second is a butanone or butane-2-one. Again, there is only one form because the other form is a mirror image of this, and its mirror image can be rotated to form this compound again, right? This is butanone. And then comes wait, I'll not write this way, write it the other way around, right? It's CH3, this is CH2, this is O, and this is CH3, right? I'll draw the CH2s over here, right? The next is pentane-2-one, that is CH3, CH2, CH2, CO, CH3, right? This is pentane-2-one. The next number is hexane-2-one, is CH3, CH2, 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 CO, CH3. See that there's 1, 2, 3, 4, 5, 6 carbons over here. And finally, it's heptane-2-one, right? It's CH3, CH2 4 times, then CO, CH3. This is a condensed formula because I'm not writing CH2 again 4 times. It is just waste of time, right? Members of the homologous series of ketones. And finally, you have the first 5 members of the homologous series of alkenes, right? The first alkene is ethene, that's CH2, CH2. The second is propene, that is CH3, CH2. The next is butene, that is CH2, CH3. Then comes pentene, right? 5 carbons. And finally comes hexene, right? Everything is 1-enes. They are all 1-enes. They are not 2-enes, they are not 3-enes, they are 1-enes, right? This is ethene, this is prop 1-ene. There's only propene, right? Because even if you shift this double bond here, that's 1. Right? This is but 1-ene, this is pent 1-ene, and what I'm going to draw is hex 1-ene. Right? This makes 4 carbons, then a CH, a double bond CH2. Right? So you have 6 carbons over here, this hex 1-ene. That settles the first 5 homologous members of each series: alkenes, ketones, and carboxylic acids. Right? That's question number 6. Question number 7. Give condensed and bond line structural formulas, identify the functional groups. Right. A, that's 2 to 4 trimethyl pentane. Right. I'll first draw the bond line formula, then I'll give you the condensed formula, and then I'll go for functional groups, if any. Right. So I'll just write them down under each heading. This is A. Right. 2 to 4 trimethyl pentane. First draw the pentane chain. Then you have 2, 2, 4. Right? 1, 2, 3, 4, 5. It's 2, 2, 4. This is the bond line formula for it. Right? The condensed formula looks like CH3. This is CH3 twice. Then it's a CH2. Then it's a CH3, and then a CH3. Right? I made a mistake over here. This can basically be written as CH3 twice, and then CH2, a CH3, and a CH3, right? Again, this can be condensed from CH3 twice, right? So basically, this carbon is here, right? If I mark this with a star, then this carbon is a star. And if I mark this with a dollar, then this carbon is a dollar, right? 3 CH3s to the star, that is CH3 twice C, CH2 over here, and then a CH attached to CH, right? That's a condensed formula. There is no functional group over here, right? There's no alkene, there's no alkyne, there's no alcohol, there's no aldehyde, nothing, right? No functional, right? B is 2-hydroxy 1 to 3 propane tricarboxylic acid, right? First things first is, right? It's tricarboxylic acid at 1, 2, 3. So you have a COOH over here. You have a COOH over here. And then you have a COOH over here, right? And this is your alcohol. But you can see that I have explicitly mentioned C's, but that should not be there in a bond line formula. This is not actually a bond line formula. This is a rough structure of what this compound is, right? 1, 2, 3 propane tricarboxylic acid and a 2-hydroxy, right? Your carboxylic acid is fine. I'll come to the functional group later. So I'll just erase this. I'll draw the proper line bonds now. First is your pin structure. And then you have a carboxylic acid over here. COH is COOH. There is some OH over here. And then you deal with 1 COOH. Right? You know that this is 1, 2, 3. propane, tricarboxylic acid, and a 2-hydroxy, right? The condensed formula will look weird here, but basically I go with COOH, CH2, and then this is a COH, COOH, and then you have CH2, COOH, right? Why brackets is because it indicates that they belong to this carbon and not this carbon. And finally, wait, no, I forgot the functional groups. And here the functional groups are carboxylic acids, that is the C dash COOH, the carbonyl group, the carboxyl group, not carbonyl, I'm sorry, carbonyl is CO, right? COOH is carboxyl group, and you have the OH as a hydroxy group, right? Your functional groups. And finally, coming to C, that's hexane dial, that is 1, 2, 3, 4, 5, 6 hexane. It's a COH over here. It's a COH over here. 1, 2, 3, 4, 5, 6 hexane dial. 1, 2, 3, 4, 5, 6. Right? Hexane dial. This is basically CHO, CH2 4 times. Because you can see this is 1, 2, 3, 4. 4 CH2s together, that's CH2 4 times. There's one CH over here. There's one CHO over here. It's not COH. COH denotes an alcohol group. CHO denotes an aldehyde. Right? Remember that. And you have only one functional group over here. That's the aldehyde group. Right? If this H is not there, but there are two like this. This is a carbonyl group. This is an aldehyde group. Right? That's just for information. Cool. Now that finishes question number 7. Now we'll go to question number 8. Right? Question number 8, I'll be giving you some extra information about all 3 compounds over here because they may be important in your future studies because you will be dealing with this compound next year in your 12th standard books. Right? So 8A, we are just asked to identify the functional groups, right? So A is, I'll draw this down, right? This is a CHO. This is an OME. This is an OH, right? This Me is a CH3 group, right? Do not worry. Me denotes a methyl group. And ET over here represents an ethyl group. All right? Those are common abbreviations in organic chemistry. Right? So instead of OME, I can write it as OCH3. Makes no difference because Me and CH3 are same. Right? So you have this as an aldehyde, this as a methoxy group, right? It's a methoxy ether, right? The functional group is an ether, but if you have to be specific, it's a methoxy ether, right? And this is an alcohol, right? ALD is an aldehyde, ALC is an alcohol, right? This whole compound is named vinyl, right? VANILLIN, right? This whole compound is named vinyl, right? Its IUPAC name is 4-hydroxy 3-methoxy benzaldehyde, right? I'm not writing it down, just saying. If you want, I'll just write it as text. 4-hydroxy 3-methoxy 4-hydroxy 3-methoxy benzaldehyde, right? That's the name of this compound. Cool. And then you have B, you have an NH2, and here you have COO, CH2, CH2, N, C2H5 twice. I'm writing it down as NET twice, right? Because C2H5 is the ethyl group, and ethyl can also be represented as ET, right? So this compound, you can see, first functional group, that's an amine, right? It's a primary, first 1-degree amine, if you have to be specific. And you have to know that this is aromatic, right? This is not aliphatic, this is aromatic. It's connected to a benzene ring, right? This group COO is an ester, right? And this is a tertiary element, right? Because it's connected to 3 carbons, two of the ethyl and one of this carbon, right? So these are the 3 functional groups over here. Tertiary amine is an ester, and this a primary aromatic amine, right? This compound is given the name procaine, right? Procaine. This is given the name procaine. Right? People may note that this compound is an anesthetic, and you usually experience this compound as a numbing agent, right? In your dentist chairs. This is very widely used, right? ATIC is an anesthetic, right? Maybe some people may have heard of the name Novocaine, right? It's usually sold under the brand name in the US, and you usually encounter it in a lot of stores. If you watch House Empty or something, you will 100% encounter that Novocaine. That's composed of this common procaine, that is this compound, right? And it has the name to in brackets, it's diethylamino thyl or amino, right? The ester takes precedence over the amine. So it's a 4-amino benzoate at first. And then you have whatever this compound is, that is NN-diethyl or 2-diethylamino ethyl, right? Because this an ethane, this becomes ethyl. This is NN-diethyl, that can be written as diethylamine. It is diethylamino attached here at the second position because this is carbon number 1, right? So I'll just display this, right? This compound, the procaine, 2-diethylamino ethyl, 4-amino benzoate, right? And finally, you have the last question, that's number C, simple. This is CHNO2, right? So for all 2 functional groups over here, this the nitro group, nitro, you can call it nitroside. Nitroside is above, right? And this is a double bond. And if you want to call it an ethylene double bond, whatever, it makes no difference, right? This compound is named beta nitrostyrene. This, given the name beta nitrostyrene, is important in polymerization because I think, wait, yeah, I don't remember what is important. I don't think it's about polymerization, but this is basically given the name beta nitrostyrene because this is the alpha carbon, this is the beta carbon for styrene, right? The alpha is whatever phenyl is attached to, because phenyl takes precedence over it, right? And this is given the it has the IUPAC name 1-nitro 2-phenyl 2 substituents. So it's basically in the order of their alphabeticals. So it's 1-nitro 2-phenyl ethene, right? Or it can be called beta nitrostyrene, right? Styrene is basically phenyl CH2 without the nitro group attached. Styrene is important in polymerization. You'll learn that in your polymers lesson. That's in 12th, right? Moving on to question number 9. Which are the following NO2s? Which are the following? This O- attached to an NO2 group, or this O- is more stable, and why? Right? Pretty easy to see. This is going to be more stable, of course, right? That is this compound. And the why is because this shows a minus I effect, while this shows a plus I effect, right? Why minus I? Is because nitro is electron withdrawing, right? So the inductive effects go this way through the saturated bonds. And so this is basically drawing electrons away from this electronegative, this negatively charged oxygen, which basically stabilizes the whole compound, right? But here, this is a carbon group attached to an oxygen. Oxygen is more electronegative, So it starts pulling in the electrons. That's a plus I effect, right? This concentrates electrons more over here, basically making this molecule destabilize, right? So this is going to be more stable. The reason is this minus sign. Question number 10, right? Explain why alkyl groups act as electron donors when attached to a pi system, right? This question, this phenomenon occurs due to a very weird thing called hyperconjugation, right? You won't see hide or mention of it in your inside your book. Basically, this is a phenomenon where your CH sigma bonds, right? They get aligned. That there are empty p orbitals in this pi system, all right? Always in a pi system there are empty orbitals. So what happens is these sigma bonds, they align with the direction this this empty orbital faces, and basically these start to overlap, right? So if there are two electrons over here, they basically start sharing themselves between this sigma bond and this empty orbital, and thereby stabilizing this this pi system, right? Because of this, these alkyl groups start having a positive plus I effect, or they start acting as electron donors into a pi system, right? This is basically due to this phenomenon called hyperconjugation, where a sigma bond starts sharing electrons with empty orbitals, right? By aligning itself, because this bond is free to rotate about its axis, right? That's the specialty of a sigma. That's question number 10 taken care of. And then one more thing to note is that it's not just this hydrogen which can perform hyperconjugation. It's all three of them, right? That is why for sometimes you'll see that in your in this kind of a system, in this carbocation system, the tertiary is always more stable because of the plus I effect that's introduced by these alkyl groups. And the plus I effect originates because of this hyperconjugation of the 9 CH bonds with this plus, right? At one time, one CH bond of this, one CH bond of this, and one CH bond of this can hyperconjugate with this plus. But since there are 3 CH bonds, each bond can basically, if I mark it as 1, 2, 3, this can basically rotate itself to make H2 at the start and H1 here, H3 here, something like this, right? C double bond C, and this can basically hyperconjugate, right? Or this can also rotate itself to form something like a C, H3 here, H1 here, H2 here, and then C double bond C, and you have a hyperconjugation of the CH3 bond, right? So basically this carbon can rotate and each hydrogen can hyperconjugate, right? So basically this kind of a structure has 3 hyperconjugated structures, one of this, and one of this, right? That is something you have to do. Very important in hyperconjugation. So into question number 11. Power resonance structures show electron shifts, right? First one, C6H5OH. Since I have to show the resonance structures, right, I'm drawing the first form of benzene. And then one electron shifts here. This goes here. It's the same, this is the same. This has a minus and 2 electrons. There is a double bond here. The O has only 1 electron pair. There's a plus and is connected to a hydrogen, right? This negative comes here. This goes here, forms this structure, that is here or here, a lone pair and a negative charge, double bond O, one lone pair positive charge and the hydrogen. This lone pair comes here, this lone pair goes here, this double bond goes here. You have then one, a lone pair and a minus charge, double bond O, single lone pair, a positive charge, dashed by hydrogen, right? Finally, this negative charge comes here. This goes up, and you are left with the second resonance form of phenol. Right. The second stable resonance form of phenol, that is 2 lone pairs on oxygen, 3 double bonds, and a single bond here. Right. That takes care of the resonance forms of phenol. Right. You can basically see it at one go. 1, 2, 3, 4, 5 of 5 resonance forms. Right. One thing to note, it's not this weight. Draw this way, then people make it confused. So just making sure that it's this lone pair that's shown and not the bond of covalents, right? Since also clean. Second is the same resonance forms but with NO2, right? NO2 is trickier because you have a datal bond with it, N, a datal bond, 1, 2, 3, double bond O with 2 lone pairs, right? Structure of nitrobenzene, right? Then nitrobenzene, what happens is first this goes here, this comes here. Maybe you can separate this after plus minus whatever, right? The bond goes here, bond comes here. You get the first resonance structure with a double bond here, a double bond N, and a positive charge inside the ring, right? You have a single bond O with 3 pairs of electrons, the minus. You have a positive charge on the nitrogen, and you have a single bond with O, and this also carries a minus charge, right? This bond shifts here to make up for this plus. You then have the third resonance form, that is 1, 2, a double bond N, plus over here, a plus over here, attached to 2 oxygens, which are both negatively charged, with 3 lone pairs of electrons, right? And then you have the fourth resonance form that occurs when this double bond shifts to make up for this positive charge. Double bond here, a positive charge here, double bond N, positive on the N, and then you have 2 O's which carry a negative charge each with 3 lone pairs of electrons, right? And finally, this double bond shifts here and 1 lone pair shifts here to give you second stable resonance form, that is 1, 2, 3, single bond N, also on the N remains, single bond to O, the negative on this O remains, and then you have a double bond O with 2 lone pairs. And there are also some other resonance forms that can be created when you look at this transition, right? Then this goes here up and one of the lone pairs comes up, right? This is also a transition that can take place. And so this also gives rise to other resonance forms. I'm not talking about, right? That's the resonance forms of nitrobenzene as be taken care of, right? And then C, you have CH3, CH, double bond CH, single bond C, double bond O, single bond H, right? And on O, you have 2 lone pairs, right? The only thing that can happen here is this pi bond shifting over here because O is electronegative and can support a negative charge on that O, right? So you have CH3, you have a CH plus, CH, double bond C, single bond O minus with 3 lone pairs of electrons and a CH3 at the edge. Only 2 forms here because there can only be a double bond shift between this and this, right? Or you can have this kind of form, CH3, CH plus, There's a plus here. CH double bond CH, single bond C plus, and then O minus, right? This can also be a form. 3 forms. D is benzaldehyde, right? First form is this separation of charges in the benzaldehyde carbon. There exists a plus, there exists a minus, 3 bonds, right? And then the double bond shifts to take care of this plus, 3 lone pairs, and the plus shifts here. This double bond shifts here, take care of the plus. O minus means that there are 3 lone pairs here. And then again a double bond shift, and the final shift, and here. That's benzaldehyde taken care of. And finally, not finally, but second last, you have plus side. So that inform because there are the resonance side. Since it's a plus, only the plus move, double bonds move to take care of the plus. First form, 2 double bonds here, double bond plus, and a double bond here. This double bond shifts, you get finally this double bond shifts back. This for the aldehyde, this for your methyl, phenyl methyl. And finally, you have this CH3, CH1CH, CH2 plus, right? Only 2 resonance forms here. This goes here, brings the plus charge here, right? Don't have any other. Sorry for that. Right? Don't have any other form. This is butyene 1-yl carbocation, right? And this is your benzyl carbocation or the phenyl methyl carbocation. You can call it the benzyl carbocation because benzyl is recommended nomenclature, right? So this has your resonance form of CH3, CH plus, CH, double bond CH2. That's 11 done. 12. What are electrophiles and nucleophiles? Explain with examples. I'll just show you in the text and I'll explain by voice what electrophiles and nucleophiles are. It's too much to actually write down here, right? So you have the nucleophiles and electrophiles thing here at 273, page number 273. You have a reagent that brings an electron pair to the reactive side is called a nucleophile, while a reagent that takes away an electron pair from the reactive side is called an electrophile, right? What basically they mean is that an attacking reagent, right? A reagent that is attacking here, a reagent that is attacking a substrate, right? If that reagent has an electron pair in excess and provides it to the substrate, it's called a nucleophile, right? While if the reagent itself has an empty orbital or has a dearth of electrons, that is, has a plus charge on it or has has a plus charge or has a free radical or has an empty orbital, then that reagent is called an electrophile because it wants electrons from the substrate and it attacks so that it attacks an electron-rich site of the substrate, right? That is the difference between a nucleophile and an electrophile, right? So basically, if I have to write it down, a nucleophile N minus is, wait, instead of doing this, I'll write down as text, right? A nucleophile is an attacking reagent that has an electron pair and donates it to the substrate. That's a nucleophile, right? Some examples of nucleophiles are your Cn minus, the cyanide ion, right? Wait, sorry, this Cn minus through C because the minus sign is over C and C is the attacking side, right? Your OH minus, the hydroxyl ion, it attacks to O because the minus charge is on O. You have your Lewis acids, that is your Lewis bases, that is H2O. There's lone pairs which can also attack sites, right? So this is this is also an attacking reagent that has an electron pair and donates it to the substrate. Right? So these are examples of nucleophiles. While an electrophile, right, the reagent that takes away an electron pair, but basically it is also an attacking reagent, but it has an empty orbital or can accept electrons like a free radical, right? So an electrophile can be defined as an attacking reagent that has an empty orbital and accepts an electron, right? So it accepts an electron pair from the substrate always. So basically something like BF3, right? Some molecule like BF3, because boron trifluoride has an empty orbital over here that can accept electron pairs, right? AlCl3 acts much the same way. You have the chlorine free radical that is an electrophile, and you have your normal plus charge species like your CCl3 minus your CCl8. That's a stupid example. You have your normal copper cations like the CS copper cation. You have your NO2 plus that acts as an electrophile. These are examples of electrophiles that you have, right? BF3, AlCl3, Cl dot, CH3 plus, NO2 plus, right? And Cl minus, OH minus, H2O, H2O are all nucleophiles, right? That is the difference between electrophile and nucleophile. Then you have question number 13. Identify the reagents shown in bold in the following quantities and nucleophiles. I think I've already taken most of these examples. OH minus is a nucleophile A. Right. For nucleophile, I'll write as N minus. For electrophile, I'll write as E plus. Right. B, Cn minus again is a nucleophile. And you can also basically see it in this example because it attracts an H plus, right? And it donates an electron pair to this molecule. Right? I mean, it transfers a negative charge to this molecule, basically making it negatively charged, making it electron rich. And so it's a nucleophile, right? It attracts this nucleus of H plus. Here again, Cn minus attracts this, it goes and sits here, right? This, the second example is basically some kind of reaction like, this is CO, this transfers here, this person attacks here, and this becomes CH3, CO minus Cn, CH3, right? And that attracts the hydrogen from the solvent most probably to become OH. This is nucleophilic addition. And you can basically see that this side becomes positively charged here when this electron pair transfers. I drew the arrow wrong. It goes here, right? And say that there develops a minus charge here, a positive charge here, and this minus this Cn is attracted towards this positively charged nucleus, right? And so this is a nucleophile. Finally, you have CH3CO plus, which is attracted to the benzene ring and basically becomes C6H5COCH3, right? Two things. First of all, a nucleophile cannot attack benzene, right? Only electrophiles can attack benzene because benzene rings are electron rich, right? And so it's basically a no-brainer that this molecule CH3CO is an electrophile. But then again, you can also see it in the sense that it's positively charged A, and B, it attacks an electron-rich centered benzene, because if you draw the resonance form, then you'll see that there is a minus charge over here, like this form. From here, you see that there develops partial negative charge over here, right? A partial negative charge. So that concludes question number 13. And then going to question number 14, classify as one of the reaction types. One nucleophile replaces another, right? Br minus is a nucleophile, HS minus is a nucleophile. One nucleophile replaces another. That is an SN, or a substitution, a nucleophilic substitution reaction, right? this can be written as B. You can basically see that this HCl adds to this double bond. But the way it adds is basically first HCl splits out, right? HCl becomes H plus Cl minus, right? It's actually reversible, but it's way towards this side, right? H plus and Cl minus. This H plus attacks the C double bond C side, right? I don't care about what's, I'll just write it as this. It basically splits up as the electron pair, right? So this becomes Me2C, carbocation formation, CH, right? It's already CH2, so it's CH3. Because hydrogen attacks this negative center. And then you have a carbocation over here, which is attacked by this chlorine, which forms Me2C, Cl, CH3, right? The first attack is by this electrophile. And so this is an example of an electrophilic addition reaction, right? An EA reaction. Then coming to C, you can see that this is an OH minus, which attacks Br, but it comes out as H2O and Br minus, and an ethene molecule is formed, right? First of all, note that this OH minus attacks and removes hydrogen from this. So this molecule is also involved in the reaction, right? And you have OH minus, of course, its concentration also affects the reaction. And so this is basically, this is an E2 reaction, right? Or the proper English name is bimolecular elimination reaction, right? Finally, you have this compound reacting with HBr to give this, right? Where you can see that here first it's a CCH3 twice, but here it's CCH3 twice, and there's the rearrangement happening, right? And there is a nucleophilic substitution at the same time, right? Because this HBr is the Br is basically substituted in place of OH, right? And so this is basically SN rearrangement. The mechanism of this reaction proceeds like basically, if you have C, Me, 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 C, CH2OH, and you are attacking it with H plus Br minus, right? First of all, the H plus attacks the electron rich side of O, becomes here it becomes CH2, OH2 plus, right? This bond breaks, and you are left with whatever carbon systems over here. I'm not drawing it, right? And then you are left with this carbon system dash CH2 plus, right? Which is very unstable. And here you have CCH3, CH3, CH3, right? So one of these CH3s come here, and the system shifts to form C, Me plus, CH2, CH3, right? And here Br minus attacks, right? And this process just disappears. You have C, Me2Br, CH2, CH3, 3C, 4, 5, 3Cs, 2, 3, 4, 5, 6. There's a mistake over here. This extra CH2 should not be added. Just make a note of, right? This extra CH2 should be added over here. Because if you can see here, there are 5 carbons, but here there are 6. That's not possible, right? Yeah. Look at question number 15. Right. Relationship between members of the following pairs. This and this are they are metamers, right? Because on either side of this ketone, the length of the carbon chain differs, right? They are at the same time, they are also positional isomers. Because this is pentane 3-on, right? This is pendant to 1. So they are also positional resonance, right? B is, this is a trans deutero compound. This is a cis deutero compound, right? D and H are not the same. You can differentiate between a deuterium and a hydrogen atom. And so stereoisomeric effects do follow over here. And so this is a trans compound, this is a cis compound, and they are stereoisomers, they are geometrical isomers, right? And finally, you have this this form and this form, right? First of all, know that no atom is changing in position, right? The only change that happens is a shift in the electrons, right? This pair goes here and the positive charge comes over here, right? So they are resonance structures. They are resonance forms. They are resonance contributors. So ABC is identified in a step. Question number 16. For the following bond cleavages, use the curved arrow notations to show electron flow, classify stabilizers or hydrolyzers. And for the reactivity. All right. A, very simple. You see that both are free radicals. So it has to be homolytic cleavage. It's also supported by the fact that on both sides is the same atom. So in those cases, the most common kind of cleavage that happens is a homolytic cleavage, right? So this becomes dot CH3, which are both free radicals, right? As the reactive intermediate. Going to be sorry for that. B, it's a ketone being attacked by a hydroxy group, right? And this hydrogen is basically extracted. Here there is carbanion. So the cleavage that is produced is CH bond cleavage, right? I'll draw the 3 CH bonds. This CH bond basically cleaves off. The carbon draws both the electrons and hydrogen is basically left out. This becomes H plus CH3, CO, CH2 minus, and H plus, which is gobbled up by this OH minus to form H2, right? So the reactive intermediate formed is a carbanion, right? And this is a homolysis. This is a heterolysis. Why exactly they can form a carbanion here is because of the resonance hybrid that forms with this, right? So that supports the formation of carbanion. Otherwise, carbanions are ridiculously unstable. They are very highly reactive. Third is this bromo compound, right? Basically cleaves like this to form carbocation here and Br minus. This is a carbocation, that's the reactive intermediate, and the bond cleavage is heterolytic, right? Finally, coming to D. D is a benzene electrophile. This is an electrophilic aromatic substitution, and EAS, if you will, right? So benzene plus this hydrogen. What happens is, take this kind of a system. So you basically have hydrogen is not affected. What is affected is the double bond. So basically, this double bond goes over here, right? In a show of heterolytic cleavage, you have in D 1, 2, 3, because this place is the one which has a carbocation, right? Plus the electrophile. This double bond undergoes heterolytic cleavage to give this intermediate species a minus a plus, double bond, right? Which basically reacts with this electrophile to give this kind of a system. Right? So this is what is formed. This is a heterolytic cleavage, and what forms finally is a carbocation. Right? This also is an intermediate because the hybrid is not fully stabilized. This hydrogen actually leaves. This again undergoes heterolytic cleavage. This hydrogen leaves, and your benzene is stabilized back. But this is also an intermediate, and this is a carbon. Right? So this is the reactive intermediate, and this was carbon. That takes care of 16. And then 17. Explain the terms inductive electron. Right. Again, what is there in the book? So you can see that this polarization of the sigma bond caused by the polarization of adjacent sigma bonds is referred to as the inductive effect. Right? This takes place solely when the chain is saturated. When there's a pi bond or something that interferes with the inductive effects. Right? So the I effect I can basically write down in text form as a permanent displacement of sigma electrons along a saturated chain in the presence of an electron withdrawing or donating. Right? Don't worry, I'll zoom in for a bit and I'll show you what I've written. So this can be explanation of what the I effect basically is. Right? I'm not said in which direction this permanent displacement occurs. If this permanent displacement occurs in the direction of the in the direction of the substituent, then it's a plus I effect, right? Otherwise, if it occurs in the direction opposite to what is the substituent, then it's a minus I effect, right? Basically, if it pushes the electrons towards the substituent, it's a donating group, it's plus I. If the electron is coming out of the substituent group, then it's electron withdrawing or it's minus I, right? That's the difference. And then you have the E effect, the electromagnetic effect, right? The electromagnetic effect is temporary and it shows only if the organic compound has a multiple in the presence of attacking reagent. This happens when this pi electron is completely transferred to one of the atoms joined by a multiple bond on the demand of an attacking reagent, right? Something like this. This is an example of the electromagnetic effect happening. Right? This is temporary because the system bounces back towards its stable state with the attack of the electrophile or the nucleophile, whatever. All right. So if I have to denote the E effect, basically I'll write it down in text form as the complete transfer of a shared pair of electrons of shared pair of I electrons. This does not occur when there is a sigma electron. So only occurs between pi electrons, right? Between two atoms linked by multiple bonds. The only thing that I've left is the temporary part, right? Is the temporary and complete transfer of a shared pair of pi electrons between two atoms linked by multiple bonds in the presence of an attacking reagent. Right. Two types, positive and negative. If the transfer is to the atom to which the attacking reagent gets attached to, then it's positive electronegative. Otherwise, it's negative electron. Right? You can also think of it this way: the positive electromagnetic effect creates a carbocation at the end of the reaction, while the negative electromagnetic effect creates a carbanion at the end of the attack. Right? This again is an intermediate stage, but you can separate this carbocation and the carbanion out. Right? So this generates a carbocation if it's positive electromagnetic, and the minus E effect generates a carbanion. Right? And coming to the rest, electron displacement effects explain the correct order facility. Right? So here you have Cl3, Cl2, Cl, 3 halides, 2 halides, 1 halide. Right? Halides always they undergo the which effect? Halides always undergo the minus I effect. So the first one, A, is explained by the minus I effect, right? It's explained by the minus I effect. Because as these halides draw electrons away from the COOH, what happens is the O minus charge that happens when this hydrogen is taken away, when the acidic behavior is actually maintained, right? If you see, this is if this is the COOH group, the acidity means that this whatever is here is stable, right? If this part is more stable, then the compound is more acidic. That's the basic theory behind it. And so if there is a larger minus A effect, then this negative charge is more drawn out, and the this compound is more stable, right? And so due to minus A effect, this is more stable. This is more acidic than this, right? P, on the other hand, is basically the opposite, right? Because it's just alkyl groups. They do the plus I effect in conjunction with hyperconjugation, right? And so if there are more hyperconjugated structures, this anion is much more unstable, right? And so this, with its larger hyperconjugated structures and the larger plus I effect that happens with each CH3 being secondary, being beta to this carboxylic acid, right? It's just one carbon behind. So this inductive effect is going to be much less than this and this. Since it's plus I, that means that electrons are pushed towards COOH, and the more electrons pushed, the more unstable it becomes. And so this is the least acidic, this is the most acidic, right? B is explained by the plus I. Right? 18 is largely theoretical, right? Give a brief description of the principles. Crystallization runs on the principle of the differential solubility of a compound and an impurity in a solvent, right? It's the different solubility of a compound and an impurity. That is crystallization, right? What happens is you make a solid dissolve at a higher temperature, right? An impure solid dissolved at a higher temperature. You make sure that the solution is saturated, right? After you obtain a saturated solution, you start cooling the solution down, right? And then what happens is you get pure crystals on the sides of the test tube, right? You filter the solution out, and then you basically scratch the sides of the test tube to get pure crystals of what compound you want to obtain. The impurities remain in the solutions, right? The example is basically the crystallization of copper sulfate, right? CuSO4.5H2O, right? That's the example for crystallization, right? What you do is you dissolve approximately 0.8 grams of copper sulfate in 8 milliliters of water, right? You add 1-2 drops of concentrated sulfuric acid. I think it's concentrated. I'm not really sure, right? You drop 1-2 drops of concentrated sulfuric acid to prevent the hydrolysis of copper sulfate, right? You then heat the solution. You leave it to cool after filtration, right? And then finally, you scratch the size of the petri dish or the test tube that you are doing the experiment in. You get crystals of copper sulfate, right? You get pure crystals. You don't just get crystals, you get pure crystals, right? B is distillation, right? Distillation works on the principle that two liquids, right? Because distillation is carried out between two miscible liquids. Distillation, two liquids with very different boiling points. Boiling point I'm representing as PP, right? They vaporize at different temperatures. Usually, to carry out pure distillation, you need a temperature difference of at least greater than 25 degrees Celsius or 25 Kelvin. Both are the same, because Kelvin is just Celsius plus 2, right? Finally, the cooled vapors are obtained and they are obtained and separate, and they form the liquids. Finally, the liquids are separated, right? It's used to separate non-volatile liquids from a volatile impurity, which is also in liquid form, when both have a boiling point difference of greater than 25 degrees Celsius or perfect, right? An example is the distillation experiment of aniline and chloroform. Basically, what happens here is that you heat this mixture in a round bottom flask. And then the first thing, first vaporizes, what first vaporizes out is chloroform, which boils at 334 Kelvin, while aniline boils at 457 Kelvin, right? So this boils off first, and to get pure vapors of chloroform outside, you run that through a condenser to obtain liquid chloroform, right? And what is left behind is liquid aniline, right? So you have a round bottom flask with aniline, with the aniline mixture, and then you have some kind of a conical flask where you obtain the results of your condenser with chloroform, right? And so you separate the two mixtures out using distillation, right? C is chromatography. Chromatography works on the principle that individual components move at different rates through a stationary phase under the influence of the mobile phase. Ready? Under the influence of the mobile phase, right? So what this basically means, what this basically means is that if you have a mixture of 2, 3, 4 things, right? They move at different rates through a solution, right? Because they move at different rates through a solution which is passed through another solution, because the affinity of each component to the two different solutions differs, right? For an example, something like ethanol is more attracted towards water than towards chloroform, right? So if you drop ethanol in a mixture of chloroform and water, then you can basically say that the ethanol is dissolved in water and not in chloroform, right? And so if you remove the chloroform layer, you won't have any ethanol in it, but the ethanol will be dissolved in water. Something like that is what happens here in chromatography. But here it's not exactly chloroform and water, but it's the stationary and the mobile phase, right? The stationary phase is just that it acts stationary. It does not move exactly in any sense, right? It's just there as a medium to dissolve and to absorb something, right? While the mobile phase is the layer that keeps moving, and the mobile phase carries your mixture of solvents, the mixture in some solvent, right? And you choose the stationary and the mobile phase such that that mixture can easily be separated out. There are different techniques of chromatography, but basically that is what this principle means, right? The stationary and the mobile phase. Under the influence of the mobile phase moving through the stationary phase, each component in whatever you dissolve inside the mobile phase gets stuck to the stationary phase, for lack of better words, right? And so you get separate components out in the stationary phase, because each component sticks to the stationary phase at different points of time, right? The example of chromatography is the separation of blue and red dyes. Separation of blue and red dye, right? What they usually do is they dip a chromatography paper, right? And then inside a solution of liquids, that solution of water and blue and red dye, I guess, right? I'm not really sure, right? What happens is by capillary action, this solution of blue, red dye, and water moves up through the chromatograph paper, right? And depending on what the paper is made of, either blue or the red dye is less absorbed, and it travels further up the paper, right? What is more absorbed stays lower and finishes off sooner, right? And so you get distinct regions of blue and red dye, and basically you can separate them out, right? That takes care of question number 18, right? Question number 19 is describe the method can be used to separate two components, different solubilities in a solvent test, right? This is basically the principle of fractional crystallization, right? In normal crystallization, you basically deal with one thing to be crystallized out. Here, you deal with many things to be crystallized out, which have not really that different varieties in building, right? So the less soluble compound crystallizes first. That's something that we know in crystallization, right? The more soluble one remains in the solution, right? After the first crystallization is done, you separate out the liquid with the second component to be filled to be crystallized. Second compound plus impurities. You carry out crystallization for this again, right? You again concentrate this compound. You again concentrate this, and the hot solution is again allowed to cool down. When the and then you basically obtain crystals of the second compound also, right? And depending on how many compounds there are, you do the same method that many times. After the first crystallization step, you obtain the first compound out, right? You obtain the first compound out. After the second crystallization, you obtain the second. After the third, you obtain the third component, etc., so on until all the different components have been obtained, right? That is how you use a fractional crystallization to separate two compounds with different solubilities in a solvent, right? Question number 20. Difference between distillation under reduced pressure and steam distillation, right? Very minimal differences, but it's something, right? This is normal distillation. This is distillation under reduced pressure, and this is steam distillation, right? This is condensation. This is a condensation by cooling, right? This is condensation by cooling to get pure liquid. Distillation under reduced pressure is actually this also the heating process is the same for all three, right? Under reduced pressure, what happens is this condensation is by cooling under reduced pressure, right? So in your normal distillation setup, what happens is you cool with the atmospheric pressure acting on it, 1 atm pressure, right? Under this is for your normal distillation. Under reduced pressure, what happens is instead of 1 atm, you do with 0.2 atm or something, right? This is because some vapors are not some liquids are not exactly stable. They again escape back to vapor, or they explode sometimes. So basically, you have to cool under reduced pressure to maintain that stability. This also can be this is also a method used to cool down liquids which have a very high boiling point, because under reduced pressure the boiling point also reduces. The boiling points also reduce, right? They are useful for this kind of liquid which has a high boiling point, or those liquids which decompose below their boiling point, right? Those for those kinds of liquids you use distillation under reduced pressure, right? Finally, steam distillation is something that how to say this? So you basically saturate the vapors above with steam, right? So if your container is here, basically everything above is saturated with steam, right? What happens here is that the partial pressure of water is drastically increased, right? And so since the vapor pressure is quite high, and the boiling point of and the vapor pressure of the liquid itself is quite low because you are saturating the vapors above with steam, what happens is the liquid boils at a temperature much lower than its normal boiling point, and hence decomposition is avoided. It's again carried out for the same methods, same things as boiling point reduction and those liquids which decompose below boiling point. But here you have the apparatus required is much more simple because you are just inundating the vapors above its steam, right? This is used to this also used to purify liquids like mercury, which is insoluble in water, right? Which possesses a very low vapor pressure and contains non-volatile liquids. Right? That is the difference between D, DRP, and ST. That's 20. Right, going to question number 21. Oh, we have just finished half of it. Done. Okay, fine. I'll rush through the rest. So I don't think there's much to go through. Right? Discuss the chemistry of Lassen's test. I ate my words. There is much to go through. Right? First one, Lassen's test deals with the sodium fusion extract. Right? You boil your basically what happens is basically what you do is to generate the sodium fusion extract, a small quantity of the organic compound basically heated with a sodium with molten sodium, right? And the test tube in which this occurs heated very strong, right? The red hot tube is plunged into distilled water, and then the contents are boiled for some time, cooled, and then filtered. Okay. The filtrate is termed as sodium fusion, right? This is also known as Lassen's test. Right. Lassen's test occurs for nitrogen, occurs for sulfur, occurs for halogens, right? For nitrogen, what happens is you boil the sodium fusion extract with ferrous sulfate, right? First, if your compound contains nitrogen, since it's organic, it also contains carbon. So this becomes NaCl, right? You first boil NaCl with ferrous sulfate, right? FeSO4, right? I'm not balancing equations, right? I'm just showing you what the chemistry of the water happens is, right? Plus FeCN2, that's done, right? And then since you are boiling it with excess of ferrous sulfate, this FeCN2 reacts with NaCN to give this complex Na4 FeCN6, right? This is a sodium ferrocyanide, sodium ferrocyanide 2. This is the Fe2. Right. Now what happens is you acidify it with H2SO4 to accomplish this this complex formation, right? And finally, you heat it. You heat the solution with concentrated sulfuric acid, right, to oxidize Fe2 plus to Fe3 plus, right? Finally, Fe3 plus reacts with the sodium ferrocyanide that's formed to give you ferric ferrocyanide. No, it's ferrous ferricyanide. It's ferric ferrocyanide. It's Fe4, Fe6 thrice, right? Ferrous or ferric cyanide. This is basically 3 plus. This is basically 2 plus, right? This complex has a Prussian blue color. It's a Prussian blue precipitate, right? So this complex, since it has this distinctive color, is also known as a Prussian blue complex, right? The complex of Prussian blue, the Prussian blue complex, ferrous ferric cyanide, ferric ferrocyanide, everything has the same meaning. Is a Prussian blue. Is this complex that generates Prussian blue, right? This is a Prussian blue precipitate. This is right. One important thing to note is that if the compound contains both nitrogen and sulfur, right? Instead of NaCN forming, it forms NaCNS, thiocyanide, right? Then this precipitate will not form, right? But what happens is on reaction with Fe3 plus, it generates this complex ion. Okay, it's not a complex. I'm sorry. It's not a complex, right? With Fe3 plus, it generates FeCNS thrice, which is a blood red precipitate. But if you want to again go with the sulfur and the nitrogen things, the nitrogen conformation again, then what you can do is you can boil the whole solution with an excess of sodium, right? Then you get then this basically, if you have an excess of sodium, then you get sodium and heat, then you get NaCN plus Na2S, right? That forms. And then finally you can basically do Prussian blue and you can do the sulfate test, sulfite test, right? Test for sulfur goes as such. What you do is you add, you acidify the solution with acetic acid first, and then you add less acetate. right? Na plus S on heating gives you Na2S as first, right? This is sodium sulfide. Sodium sulfide, you acidify the solution and you add lead acetate, because lead acetate is normally sparingly soluble in water, yes, right? CH3CO twice in the presence in an acidic solution. What happens is it forms lead sulfide precipitate, which is black in color. All right. So this is a very good acid test for sulfide. But if you don't want to do it, there is also another test where you react sodium sulfide with sodium nitroprusside, right? What happens is that creates a violet color. Violet coloration in the solution. It's not a precipitate; it's a violet coloration, right? It's a purple violet coloration actually, right? FeCN5NO. I'm not writing the counter ion. I'm not writing Na because that frankly does not matter here, right? This is the nitroprusside ion. If I add Na2 over here, that becomes sodium nitroprusside, right? When it reacts with the sulfide ion, what happens is you get this complex, right? Consider this to be drawn from the solution, right? FeCN5 NO.S, right? This is a 4 minus ion, this 4 plus, it's counterbalanced. And this complex has a purple violet coloration, right? I repeat, this is not a PPT. This is not a precipitate, right? This has a purple violet coloration. This is also an acid test for sulfur. If you have a violet or a purple coloration with sodium nitroprusside, then it means that sulfide ions are present in your solution. All right. Finally, coming to the test for halogens, right? Test for halogens is pretty simple. You take the sodium extract, right? NaX, where X is a halogen, right? It's a chlorine, bromine, or iodine, right? This you acidify with HNO3 and you add AgNO3, right? What happens when you acidify with HNO3 is that any nitrogen or sulfur or phosphorus that's present in the solution gets oxidized to NO2, SO3, whatever, and it just escapes out as a gas, right? And what is left is a halogen, and your sodium reacts with the halogen to form sodium salt. This in reaction with AgNO3 in the presence of dilute HNO3, very minimal acid, right? Very minimal acid gives a precipitate of AgX, right? This can take three forms. It can be white, it can be dull yellow, or bright yellow, or cane yellow, right? Right. Each of these three, they determine different things. If it's a white precipitate that is soluble in ammonium hydroxide solution, it indicates the presence of Cl minus as X. Right? This means that X is equal to Cl minus. If it's a dull yellow, that this is a bromide ion, right? And finally, if it's cane yellow and it is insoluble in ammonium hydroxide, this means that it is iodine. It's iodide, right? This means that X is I minus, this is X is Br minus, this X is Cl minus, right? That is the chemistry of the Lassen's test, right? And then 22 is the differentiation between the principles of estimation of nitrogen in an organic compound by the Dumas and the Jandal's method, right? So the Dumas and the Jandal's method, they differ basically in the fact that I'll just go through the process. Okay? I'm not writing down anything. I'll just give voice. In Dumas method, you have a known mass of the compound heated with an excess of copper oxide in an atmosphere of CO2 when the nitrogen is converted to N2. Right? The dinitrogen gas by itself is collected over water, and the volume is then converted into standard temperature and pressure, and the percentage of nitrogen is determined by applying the equation for Dumas, right? For Dumas method, the equation is that percentage N equals volume of N2 collected at STP divided by mass of the substance taken. The net mass M, mass of substance taken, the mass of substance OC, right, into 28 divided by 22,400, right? Because this is volume in milliliters, right? These many milliliters occupies 1 mole at STP, and 1 mole of N2 has this mass, right? We are basically converting milliliters into grams, right? This into 100, right? You collect NTP at standard temperature and pressure by reacting the compound with excess of copper oxide in Cu, right? In Gelnall's method, what you do is you digest the organic compound in concentrated H2SO4 in the presence of potassium sulfate and a little copper sulfate or mercury as a catalyst, right? In a special apparatus called the Gelnall. What happens is the nitrogen is converted into ammonium sulfate quantitatively. Finally, this ammonium sulfate is boiled with excess of NaOH to liberate ammonium gas, which is absorbed in a known excess of standard acid like HCl or H2SO4. It happens finally in your Zelda's method. It's much like titrations where you determine the percentage N as 1.4 times in molarity into the molarity of the acid into the basicity of the acid, right? The number of hydrogen ions that the acid can give properly into the volume of the acid used divided by mass of the substance taken, right? This 1.4 this 1.4 comes from the nitrogen and the into 100 that you do, right? This is for conversion of the MV, this moles into grams, right? Because gram by gram can only be a percentage, it can be something else by grams, right? That is the difference between Dumas and Gelnall's method, because in Dumas method, you heat with copper oxide, get nitrogen, you absorb nitrogen into water, you absorb nitrogen over water and convert the number of nitrogen moles into grams and then find the percentage of nitrogen. In Gelnall's, what you do is you convert it into ammonium sulfate and then from there you get ammonium. From ammonium, you titrate it with a known acid and then from the known acid, you get a percentage. Question number 23. Discuss the principle of estimation of halogen, sulfur, phosphorus present in an organic compound. Halogen, sulfur, and phosphorus, halogens and sulfur are basically estimated through the Carriers method, right? CARIUS, Carriers method. Right. In Carriers method, basically what you do is for halogens, you react the given organic compound with an excess of fuming HNO3, right? Fuming HNO3. That is fresh concentrated nitric acid, right? You do it in the presence of AgNO3. What happens is every impurity like nitrogen, sulfur, etc., and carbon escapes into the atmosphere in their oxidized form CO2, NO2, SO3, etc., etc., etc. Right? And water is H becomes H2O gas. That also escapes out. Right? Finally, you are left with an AgX. And I've already told you how you determine what AgX is based on the precipitate. Right? You collect it, you filter, wash, and dry, and then you measure the mass of AgX. That becomes M1. Right? M1 is the mass of the precipitate. M is the mass of the given organic compound. Right? Mass of given OC. It's not molar mass, it's the given mass, right? So basically, finally, in the Carriers method, you do percentage X equals the atomic mass of X, the atomic molecular mass or atomic mass of the halogen X into M1 divided by the mass of AgX into M. This whole thing into 100 gives you the percent, right? That is for halogens. For sulfur, the same Carriers method carries over. You react the OC with fuming HNO3. You get H2SO4, right? And then what happens is, wait, here you won't have NS. You will actually separate this out, and then you'll perform carries method, right? So carbon dioxide and water escape out. If there is sulfur, then you get H2SO4, right? You add excess of BaCl2 solution to this, that is barium chloride solution. You get barium sulfate precipitate. That's white in color, right? That's pure white, right? You filter wash, dry this precipitate again, and then you measure the number of grams. As above, the same convention applies. M1 is the mass of the precipitate, and M is the mass of the given organic compound, right? Finally, the amount of sulfur that's present, that is percentage S, is given by the formula 32 by 233. This is the mass of sulfur. This is the mass of barium sulfate, right? 32 by 233 into M1 divided by M into 100, right? That gives you the percentage of sulfur, right? Finally, coming to phosphorus, the estimation of phosphorus is not under any given name like this, right? There are two methods. I'll be discussing just one, right? What you do is a known mass of the organic compound reacts with HNO3. Again, it's fuming HNO3, right? This gives you H3PO4, right? Phosphoric acid, it's phosphoric acid, right? Orthophosphoric acid, say, if you want to be more precise, right? Then you treat this, the obtained phosphoric acid with ammonia and ammonium molybdate, right? NH4 twice, MoO4, ammonium molybdate. What this does is you get the complex NH4 thrice PO4 dot 12 MoO4, right? This is a canary yellow precipitate, a bright yellow precipitate, right? You can see it if you do it in your labs. You'll get a very bright yellow precipitate if you're lucky enough to have ammonium molybdate in your lab, right? And then you filter wash, try this out, and then you estimate the percentage phosphorus with a formula 31, which is the mass of phosphorus, divided by 1887. That's the mass of it's 1877, right? That's the mass of ammonium molybdate, right? This precipitate has a molar mass 1877 into M1 divided by M into 100. Those are the principles of estimation of halogen sulfur phosphorus, right? Question number 24. Principle of paper chromatography, right? Elmore, page 284. So basically, paper chromatography is an example of partition chromatography. What happens here? I'll just select till here, right? Because they have the necessary principles, right? Firstly, the exact answer is that paper chromatography is based on continuous differential partitioning of components of a mixture between the stationary and the mobile phases, right? What does this mean? Right. First of all, note that paper chromatography is a type of partition chromatography where you use a special quality paper known as a chromatography paper, right? This is basically made of cellulose, right? It contains water trapped in it, which acts as a stationary phase. This water is both situated in the empty spaces between two cellulose fibers and is chemically bonded to the cellulose fibers themselves, right? Both these types of water they make up the stationary phase, right? What happens is and finally the liquid mixture that you use is the mobile phase, right? So this solvent is a mobile phase. This paper is this paper contains water that is a stationary phase, right? As the solvent moves, when the strip of chromatography paper is suspended, this solvent acts as a mobile phase, and this solvent rises up the paper by capillary action and flows over each spot, right? Now, as a solvent moves, the different components move at different speeds. That's the principle of chromatography itself. So these components, they distribute into the stationary phase at different speeds based on the affinity to the stationary the mobile phase, right? Because the ink spot or the spot of the mixture moves differently through the stationary and the mobile phase, right? It moves at different speeds. And so the absorption level and the level of attraction and the level of dispersion into the stationary phase from the mobile phase also differs, right? If the affinity towards the mobile phase is lesser, right, the component is more going to go towards the stationary phase and stay there instead of going through with the mobile phase upwards through the capillary action, right? If the affinity towards the mobile phase is much more, then it's not going to go and sit in the stationary phase, but it's going to remain with the mobile phase and it's going to move up, right? So the different levels of affinities towards your towards the stationary and mobile phase. That is what differentiates. That's what makes this differential partitioning possible, right? It's a continuous process because as and when the solution moves up through capillary action, at each and every point, this partitioning is going to try to occur, right? If the affinity is going to be more, then the solution is going to start dispersing and the component is going to start getting absorbed or adhered to the stationary phase there and it's going to remain. It's not going to move up. So this sort of continuous differential partitioning is what they mean when they say that the principle is based on this partitioning between the stationary and the mobile phase, right? That is question number 24. And again, there's nothing to write down, so I'm just marking an X over here, right? Question number 25. Why is nitric acid added to sodium ethoxide before adding silver nitrate for testing halogens, right? It's boiled with nitric acid to decompose NaCN and Na2S if they are present, right? Because if they are present, then NaCN or Na2S for that matter, Na2S also, they react with AgNO3 to form NaNO3, right? Which interferes with wait no, it's boiled with HNO3 to give NaNO3, right? And HCN gas which evolves out or sulfur gas which evolves out, right? Or hydrogen sulfide which evolves, right? This is why it's basically boiled with HNO3 at the start, right? If this is not done, then your NaCN is going to react with AgNO3 to give AgCN, right? Silver cyanide, which is a white precipitate, which is a false positive, right? And sodium sulfide reacts with the same AgNO3 to form Ag2S, which is a black precipitate, right? This is also a false positive, and you will waste time figuring out where you did wrong, right? That is why you boil it HNO3 so that both the cyanide ion and the sulfide ions get escape out in the atmosphere as gases. That is why nitric acid is added. Right? 26. Explain the reason for the fusion of an organic compound with metallic sodium for testing nitrogen, sulfur, halogens. Right. So the reason, again, I'm not going to write it down. It's very basic. Right? The organic compound is fused with sodium metal to convert these elements to ionic form, right? Because in an organic compound, what happens is NXS, phosphorus also, they are present in covalent forms, right? So you basically want to change the sulfur to an ionic sulfide form. You want to change halogen, which is covalently bonded, to a halide form. You want to change nitrogen, which is covalently bonded, to a cyanide form, right? Because these ions have their own confirmatory tests that can be performed, right? That is easier. So you react, you boil it with sodium metal so that this covalent atom can be converted to their ion forms, right? The presence of sulfide, cyanide, and halide ions can thus be tested by using suitable reagents as per their conformity test that we have learned under quantitative analysis, right? Or in the labs. Right. 27. Name a suitable technique for the separation of components from a mixture of calcium sulfate and camphor. So, a mixture of calcium sulfate and camphor can be separated in two methods, right? A, you can do, you can notice that camphor, right? That camphor, HOR, camphor is sublimable. Camphor sublimes out, right? While, what's the other? Calcium sulfate, right? While calcium sulfate is not sublimable, right? Therefore, just if you take the mixture in a petri dish, you heat it, and then you collect the vapors and you cool it down. What happens is you will get a calcium sulfate in your petri dish, the original dish, and in another test tube or wherever you actually solidify it, you get camphor. Or you can do it by sublimation through the sides of a funnel. You get camphor sediments on the sides of it. So you can scratch through them. And that is one way of separating, right? Sublimation test, sublimation, heating, whatever you want to call it. They're the same. You can do that, right? Heat or sublimation. That is method A. Method B is that you notice that camphor is soluble in organic solvents like CCl, right? But calcium sulfate is not. Therefore, dissolve the mixture in CCl4, dissolve in CCl4. You'll notice that a CaSO4 is a precipitate, or CaSO4 does not dissolve basically, and the whatever filtrate that you have, when you filter, dissolve and filter, right? Whatever filtrate you get, that is CCl4 with a camphor. Whatever residue you get on the filter paper, that is calcium sulfate, right? Then you just boil off CCl4 properly, you get camphor. Boil off and same result. That is question number 27 taken care of. Question number 28. Organic liquid vaporizes at a temperature below its boiling point, instant distillation. Right? Here you have to notice the mechanism of heat. Right. You have steam that is inundated into the atmosphere. Right. So here what happens is the vapor pressure of water on the boiling point is very high. Right. And the vapor pressure of the organic compound is very low. Right. It's low compared to the vapor pressure. Right? Because you are inundating it with steam. Steam is basically a water vapor. So the vapor pressure of water is basically the vapor pressure of the external steam, as well as the vapor pressure of water that escapes from the mix. Right? So this net vapor pressure plus the vapor pressure of whatever compound, whatever organic compound we take, that has to be equal to atmospheric pressure for the mixture to boil. Right? That is the principle of boiling. Right? So in this, under this condition, right, you have a very less vapor pressure needed for the organic mixture itself to boil, and so the boiling point of the organic liquid is drastically reduced because you drastically increase the vapor pressure of water externally. Right? That is the principle of steam distillation, and that is why organic liquids vaporize at a temperature below their boiling points at a steam distillation, right? Because of the partial effects of the vapor pressures themselves. Right. That is question number 28. Question number 29 is explain will CCl4 give white precipitate of AgCl on heating with silver nitrate, right? Silver nitrate test, you always have to note that silver nitrate test only works with chloride ions, right? It does not work with CCl covalent, right? This does not work. Therefore, since CCl4 is completely covalent, it does not give a white precipitate of AgCl on heating with silver nitrate. The answer is no, right? Because you cannot ionize CCl. Can't give CCl3 plus and Cl minus. That's not possible, right? Question number 30. An organic a solution of potassium hydroxide used to absorb carbon dioxide evolved during the solution of carbon present in organic. This is because A, carbon dioxide is acidic, right? It reacts with strong base to it reacts with KOH to form K2CO3, which does not react anymore, which is inert. right? And K2CO3 has decent enough molar mass that you can estimate its mass properly and easily, right? And then you can basically measure the difference in mass of the U tubes containing KOH. This measurement can be done easily because K2CO3 has a decent molar mass, right? And from this mass, you can estimate the pressure percentage of carbon by the formula. Percent C is equal to 12 by 44. That is the mass of CO2, right? Because one mole of CO2 gives 1 mole of K2CO3, right? It's 12 by 44 into mass of CO2 formed, that's M, that's M1, divided by the mass of substance taken, that is M, into 100, right? M1 is mass of CO2, M is mass of the original component or the original organic component, right? That is how you measure, that is why you use the solution of potassium hydroxide to absorb carbon dioxide. 31. Necessary to use acetic acid and not sulfuric acid, right? If H2SO4 was used, lead acetate itself reacts with H2SO4 to form lead sulfate, which is a white precipitate, right? And that gives a false positive, right? Because Pb acid twice acetate, lead acetate plus H2SO4 gives PbSO4 as a precipitate. This is white, right? This gives a false positive, and you may report the presence of sulfur when there is no sulfur also, right? That is why you use acetic acid with lead acetate and not sulfuric acid with lead acetate. 32, right? These are the set of numericals, right? An organic compound contains 69% of a carbon, 4.9% hydrogen, remaining being oxygen, right? Calculate the masses of carbon dioxide and water produced when 0.2 grams of the substance is subjected to complete combustion. Cool. So you are given that an organic compound, right? If you have 100 grams of this organic compound, then basically 69 grams of it is carbon, 4.8 grams is hydrogen. The rest, that is, it's 24.2 grams of oxygen, right? That's 100 grams of the organic compound, right? So in 0.2 grams, this is basically divided by 500, right? So I don't actually need to do this. What I can do is use the percentage carbon and the percentage oxygen formula, right? We know that percentage carbon is basically 12 by 44 into mass of CO2 formed divided by mass of organic compound taken into 100, right? The same way, percentage hydrogen is basically 1 by 18 into mass of water formed by mass of organic compound taken into 100, right? It's not 1 is 2 because you're dealing with H2, right? So you have this is 69 equals 12 by 44 into M by 0.2 grams into 100, right? Which yields me M equals 0.506 grams, right? Similarly, I'll use 4.8 equals 2 by 18 into M divided by 0.2 into 100, which yields me, this is McO2 and this is MH2O. This equals 0.0864 grams, right? That's what they've asked for. So you don't really need to calculate the number of moles of hydrogen, carbon, and oxygen. You can directly use the formula to get the MCO2 and MH2, right? And you take 2 here, because for each molecule of water formed, you use two molecules of hydrogen, right? That's 2 into 1, basically. All right, that is question number 32. Then 33. You have 8 questions left. Wow. A sample of 0.5 grams of an organic compound was treated according to Zelda's method, right? You have M equals 0.5 grams. Ammonia evolved is absorbed in 50 ml of 0.5 mH2SO4, right? The residual acid required 60 ml of 0.5 m solution of NaOH for neutralization, right? We know that one milliliter of this 0.5 molar H2SO4 requires 2 milliliters of 0.5 molar NaOH for neutralization, right? Because the molarity is the same, and NaOH neutralizes one molecule of NaOH neutralizes one molecule of HCl, right? That is half a molecule of H2SO4 if half a molecule is theoretically possible, right? So basically, 60 ml of 0.5 molar solution of NaOH translates to 30 ml H2SO4 being left out, right? Because 30 ml H2SO4 gives me 60 milliliters into 0.5 molar of H plus, right? Or it's more secondly, it's 2 into 30 ml into 0.5 molar. That is 30 millimoles H plus, right? And 60 into 0.5, this is 30 millimoles again. So I get you have 30 ml of H2SO4 is left, right? Ammonia evolved is absorbed in 50 ml, right? Since there is 30 ml left, the ammonia dissolves in 20 ml of 0.5 molar H2SO4, right? So basically, this is 20 into 0.5 into 2, that is 20 millimoles of H plus. And since one NH3 reacts with one H plus, you have 20 millimoles of NH3 being produced, right? You have 20 millimoles of NH3 being produced. So you have 20 millimoles of NH3, right? So finally, what is this? You have since one millimole of nitrogen generates 1 millimole of NH3, right? Quantitatively. This means that there is 20 millimoles of N in given mass, right? 20 millimole of nitrogen means that the mass is basically 20 milligrams. This is 20 into 14, right? Because the molar mass of the atomic mass of N is 14, right? And so you have 14 those are 28. That's 280 milligrams, right? Finally, percentage nitrogen is basically 280, the amount of the grams of nitrogen in the compound divided by milligrams divided by 0.5 grams, right? That's basically 500 milligrams, right? Into 100. This is basically 56%, right? That's your answer. You have 56% of N in the compound, right? 34. 0.378 of an organic chloro compound gives 0.574 grams of silver chloride in carrier estimation, right? The direct answer to this, right, with MnM1, as I've discussed earlier, is that percentage chlorine equals the molar mass of chlorine, that is 35.5, divided by the molar mass of AgCl, that is 143.5, right? Because the molar mass of Ag is 108. It's 108 grams. You'll do well to remember this. This is a well-known result, right? The molar mass of Ag is 108 grams is silver, right? The mass of chlorine by molar mass of AgCl into the mass of AgCl evolved, that is 0.574 divided by the mass of compound taken, that is 0.378 into 100, right? That is a direct formula for the carrier estimation. This equals 37.566, percentage, right? Just give me a moment. I'll check my calculation. 4 by 0.378. Right. It's 37.566%. Right. That's the answer. Right. Direct question. Then question number 35. In the estimation of sulfur by the carriers method, 0.468 of organic sulfur affords 0.668 of barium sulfate. Find out the percentage of sulfur. Right. Again, direct formula. Percentages is equal to 32 by 233. Right. Mass of sulfur, mass of barium sulfate, molar mass into the precipitate, the mass of precipitate obtained, that is 0.668 divided by the mass of organic compound taken, that's 0.468 into 100, right? Which is basically 19.6, right? Again, this is a direct form. Give me a moment. Into question number 36, right? In the organic compound, the pair of hybridized orbitals involved in the formation of the C2C3 bond, C2C3, right? Here, you have to be very careful. Right? When a double and a triple bond both are present in a molecule, always the end with the double bond counts as the first carbon, right? It's 1, 2, 3, and it's not, it goes this way and it does not go this way. This is wrong, right? This is correct. Right. So basically over here, this is carbon 1, this is carbon 2, this is carbon 3, right? So the hybridized orbitals involved in the formation of this bond is basically, here it's sp2, here is sp3, and so it's an sp2, sp3, that's option C, right? In the Lassen's test for nitrogen, the Prussian blue color obtained is due to the formation of, I've told you this, is basically ferric ferrocyanide, right? It's Fe4, wait, it's Fe4, Fe3, FeCN6 thrice. It is option B, right? Fe3 plus Fe2 plus ferric ferrocyanide. Which of the following carbocation is most stable? Everybody knows this. A tertiary carbocation is the most stable. This primary, no, this primary, this secondary, this tertiary. B is the answer, right? Everybody knows this. The best and the latest technique for isolation, purification, and separation of organic compounds. Latest technique is chromatography, because chromatography is what is most sophisticated. Perfect. Right. Third line is this is the answer. Right. And the last reaction, CH3CH2I plus KOH aqueous, this CH3CH2OH plus Ki is classified as. For this question, I'll actually draw the reaction mechanism because there is something. So you have CH3CH2I, right? And you are reacting it with OH minus. I don't, this K does not really make a difference unless the only difference is that the only difference between NaOH and KOH is that this is a stronger base, right? So this gives OH minus ions more readily, and so this hydrolysis is carried out more effectively. That's the only difference. Otherwise, there's not much difference, right? So in KOH, what happens first is this bond cleaves because of the presence of this base. So this becomes CH3, CH2 plus I minus. This actually does not happen this way. Bond cleavage is not fast. This happens simultaneously, right? So you'll notice that it's basically forming partial bonds with both OH and I. This carbon is attached to five atoms over here, right? Which is not sustainable, but this is a reaction intermediate, right? This cannot be obtained out, but this is a reaction intermediate, and I'll tell you why this happens also, right? And then this bond cleaves, it leaves, this comes inside, and so you have CH3, CH2OH plus I minus, and since you have K plus ions in the solution, one K plus comes in sits for the I minus becomes Ki, right? That's what happens. This reaction step is called an SN2, a bimolecular nuclear substitution reaction, where the bond cleavage does not happen first because this bond is pretty covalent, right? It's not very ionic. Unless and otherwise this OH minus comes and attaches over here, this bond cannot break because the OC bond is much more stronger than the CI bond, but the CI bond is much more covalent, and so it can only undergo homolysis, not heterolysis easily, right? The influence of this OH minus is needed for this to undergo heterolytic cleavage, and that is why this intermediate component is formed, right? Since this is SN2, this is an example of nucleophilic substitution. So B is your answer. Thus finishes the 40 questions of general organic chemistry or specific means organic chemistry basic principles. Finally, I'll stop sharing my screen right now. Hope you'll enjoy the session. Thank you for listening to me. Take care.